Molarity is the go-to concentration expression for chemists. Molarity is represented with a capital M, and it is the mole of solute per liter of solution. So, if we would have a 0.50 molar sodium chloride solution, that would literally mean there's 0.50 moles of sodium chloride per 1 liter total of solute and solvent volume. Okay, so it's not just volume of solvent, it's solute and solvent. Now, why is molarity kind of the go-to for chemists? Well, it's expressed in moles of solute, and just think of all the relationships that moles involve and get us to. And usually solutions are ultimately liquid, and so we would be measuring their quantity in liters, and so this is just very practical and very applicable. All right, so let's look at some of the questions here. So first, we're asked to provide the concentration of each species in solution. So another question I could ask is, what exactly is in your beaker as far as the chemical specific particles? Well, lead 2 nitrate, ionic. And if you're told it's a solution, then we know it's soluble. So this PbNO3 being ionic, we know it will dissociate to cation and anion, and there's 1 lead 2 for every 2 nitrates. All right, if I am 0.25 molar in this, well, for every one of these, I get 1 lead ion. So the concentration of this will also be the concentration of my lead. But for every one of these, I get 2 nitrates. Remember, the only thing that's conserved is mass and energy. There's no law of conservation of molarity. It is based upon the ratio interpretation of our formula. All right, well, let's move on to the next. We have CH3OH, covalent. And what do we know about covalent? Does not dissociate, does not ionize. If I'm given the concentration, oh, it's not minute, but I know for every one of these, that will give me just 1 solute particle. And so the concentration of this will be the concentration of this. Now, whenever we are expressing concentration in molarity, we can identify the solute and place it in brackets. So I could say that is the concentration of CH3OH, not parentheses, square brackets. We are detailed in chemistry. Okay, so we've answered that. All right, next question. Determine the number of moles of acetate ions in 50 milliliters. I am a writer-downer problem solver. You never have to write down your givens. I do some often, and that just helps me focus and just find direction in my problem solving. So I'm given 50 milliliters of my iron 3 acetate solution. So this is 50 mils of my solution. And my solution is 0.010 molar Fe C2H3O2 3. Okay. I want, at the end of my problem, to get mole of just the acetate. But I'm starting with volume of solution and molarity. Whenever you have multiple givens, I would always pause and just ask, could any of these givens be rewritten as a conversion factor? Well, volume, that's a one-dimensional measurement. Volume is volume. I mean, volume is length times width times height fundamentally, but this isn't a derived unit. But this is. Molarity is mole of solute per liter of solution. I can rewrite this to a direct interpretation of what this means. This means I have 0.010 moles of FeC2H3O2 in every, and this has 2 sig figs, so I'm just going to write 1.0 liter of my solution. So now I have this given and this given. All right, let's see where this takes us. Now, you could start with either given, but I'm going to favor starting with my non-conversion factor. So I start with 50 mils of my iron 3 acetate solution. All right, well, I know I want just moles of the acetate. Well, this will get me moles of the entire solute, but that's per liter. Oh, so if I convert from mils to liter, then use my molarity. Okay, now I'm in terms of just my solute. And I know I can interpret that formula. For every 1 mole of FeC2H3O2, there are 3 moles of acetate. Now this will not limit. I have 2 sig figs and 4, but I'll be limited to 2. And the answer here is 0.0015 mole of acetate. And for that small a volume and that low of a molarity, that is definitely a reasonable answer. Okay, now taking a look at our next setup. Okay, in this problem, I want to know my mass of sodium hydroxide that I have in 150 milliliters of a 0.2 molar sodium hydroxide solution. Ionic, so I actually know, right, this will be dissociated as separate sodium ions and hydroxide ions. So I'm actually 0.2 molar in sodium ion and 0.2 molar, in hydroxide ion. All right, same thing. Volume, not a derived unit, a fundamental unit, but molarity. I can rewrite this okay, so I have a conversion factor and then a volume. And this, of course, is the solution. Okay, let's dig in. There's my solution. Let's see. Let's get to liters. And that will get me moles of my solute. And then I know if I have moles, I can get myself to grams. Nice and easy. And we get 1.20 grams of sodium hydroxide. 4 sig figs and 3. We want to report that to 100 sig is 4, so that's what limits our sig figs. Okay, now, I trust you, ladies and gentlemen, that, what if we were just asked for grams of sodium ion? Well, if you can see that this is a ratio of 1 to 1, this molarity will be 0.2 molar of just the sodium ion. Now, what we could do is say, okay, put 2 moles of NaOH in every 1 liter of solution, and then for every 1 mole of NaOH, it's 1 mole of Na plus to get that. But I think we can make that jump just, mentally. All right, one more thing to consider. Okay, dilutions. Remember, oftentimes, just for good, just financial consciousness and responsibility, you often order from a chemical supply company concentrated solution that then you pull from for your lab work and your research. For example, when we order hydrochloric acid, it comes in 12 molar quantities. That's just sense for us to use or pull from. Nitric acid is 18 molar, actually. All right. But very rarely do we use these concentrations. When we're first doing titrations and honors, we're usually working with 0.1 molar hydrochloric acid. So it's up to us to be able to dilute. And how do we dilute? But we add solvent. All right. There's a wonderful equation that we are going to call our dilution equation. M1V1 equals M2V2. We are only going to ever use this for dilutions. Dilution equation. All right. So, what if we're working with 12 molar hydrochloric acid and we want to make, let's say, 650 milliliters of 0.1 molar hydrochloric acid? How will we make it? Well, how about let's say what we want to make is 2. So I want to make 12 molar. Okay. I'm sorry. I want to make, very sorry. I want to make 0.1 molar, and I need 650 milliliters of that 0.1 molar. Well, I have 12 molar HCl. All right. So, how do we know when we're doing a dilution or when we involve this equation? We will rely on this when we are making a lower concentration of a solute solution from a higher concentration of the same solute in solution. Or you're being asked to find a volume of either a solution you're making of lower concentration or the volume of the solution of the higher concentration. But the crux of it, how we know that we use the dilution equation, is it's the same solute, but we're just differing the concentration. All right, so obviously here we're looking for V1. So if we take our 0.1 molar HCl times the volume that we're trying to make divided by the 12 molar. Okay, now I know molarity is mole per liter, so is it okay that this volume is in mils? Absolutely, because these cancel. So if I would do, shucks, I made this up out of my head. Oh, phooey. Of course, I need to scrounge for my calculator. And I will have 3 sig figs. So, all right. So, what I get is 5.42 milliliters. But milliliters of what? Remember, I was solving for V1, and that matches the 12 molar HCl. Okay, well, is that it? Do I just measure this out? 5.42 mils? Well, of course not. It's not of this concentration, and until I add solvent. So this is how much of the stock solution you would measure. The difference, the dilute volume minus the concentrated stock volume. Now I'm subtracting here, so I would respect the least precise decimal place. And I need to add 644.6 milliliters of solvent, which I would assume is water here unless otherwise told. So the recipe would be 5.42 mils of the stock plus 644.6 milliliters of the solvent. Okay, that's the dilution equation and some basic molarity.